So as you can see, if this was a person, this would be indicating how close you were. I've just picked up a HM10 Bluetooth module. I guess I've been inspired by some of the Bluetooth-enabled proximity sensors that have been developed for social distancing applications. So inspired by these products, what I thought I would do is see if I could use my HM10 Bluetooth device to see if I can build a Bluetooth proximity sensor, because what you can do is use the RSSI signal strength indicator within a Bluetooth chip as a proximity sensor, so it can tell you how close you are to another Bluetooth enabled compatible device like a mobile phone. So I thought this would be a very interesting project. I'm going to use my HM10 Bluetooth module in conjunction with my DE-Nano board. So this is a good chance to practice maybe implementing an embedded processor on the DE-Nano, and also some custom logic for utilizing the LEDs as some kind of gauge to tell you how close you are to another Bluetooth device. So, right off the bat, I would say using an FPGA for this application is not the best idea, because obviously you would want this to be battery powered, and FPGAs tend to be very power hungry. But what the heck, I thought I'd give it a go anyway. Gives us a chance to develop something in the FPGA, and we might learn a few things along the way. So let's give this a go. One of the interesting new features in the Bluetooth Low Energy standard was the introduction of beacons. Basically, a Bluetooth beacon is a small radio transmitter which periodically transmits low energy Bluetooth signals to the immediate area, which can then be received by other Bluetooth devices to trigger various actions. Now, the core purpose of this technology was undoubtedly commercial, targeted ads and that kind of thing. But recently we've seen the use of this technology for proximity sensing. It turns out that a Bluetooth receiver is capable of estimating the received signal strength, a value known as RSSI. And from this you can estimate the distance between your own location and that of the transmitter. And given that most people these days have mobile phones with Bluetooth low energy devices installed, we've seen many researchers and companies trying to develop social distancing apps to alert users of any breach of social distancing guidelines. And since the beacon also transmits a unique code, it's also possible to cross-check with a database to see if you've been exposed to someone who is infectious. Of course, this raises privacy concerns, but there's no doubting that this is really cool technology. So this is the datasheet for the HM10. And if we look at the module itself, we can see that it only has 4 pins coming out of the module. It actually has 6 pins, but we've only got access to 4 pins here. And those pins are VCC, ground, power the device, and then we have receive and transmit. And it's pretty clear from looking at the datasheet that we will need to send serial commands into this device in order to program it into the correct mode. So here is the Bluetooth module, and you can see here I've actually dusted off an Arduino Uno. Now, I have no intention of using this in the final device, but it is a convenient way to generate serial commands. So what I'll do is use this Arduino just to generate some serial commands, see if we can program the Bluetooth module into the correct mode, and then have a look what commands it's sending back into the Arduino Uno, so we have a good idea what we're playing with when we move the development over to the Arduino Uno and the embedded processor on board the FPGA. But for now, I'll just use the Arduino Uno and see what we get. So I've written a very simple sketch here in the Arduino IDE. And I've basically tried to follow the advice in the user manual for the Bluetooth module. So I'm sending these commands So it's AT plus roll and AT plus IMME. And then I'm attempting to put the device, to make the device do an iBeacon device discovery scan. And what I'm hoping is that my mobile phone, which is behaving as an iBeacon, will be discoverable from this device, and it will give me the information from the phone, so the MAC address and the RSSI. So that's my starting point here. Okay, so I've opened the serial monitor here, so hopefully that's going to pick off any serial data being read back in from the Bluetooth module. And just as a reminder, I'm hoping to see the address of my iBeacon from my app, and also the RSSI as well. So just going to reset the sketch, and we got some information. So we can see this is actually picking up other Bluetooth devices in the vicinity, which is to be expected really. But the one that my mobile phone has, just confirm, it's this address. It's this address. So let's just have a look to see if it's given a this should be the RSSI, so minus 63 dBm. So, if this is predictable, what I'm thinking now is if the information coming out of the module always has the same length, okay, so the same number of characters, it should be fairly trivial for any piece of code running on my DE0-Nano, the embedded processor on the Nano, to basically pick off this number here, which is the RSSI number. Is basically the signal to noise ratio of the signal arriving at my Bluetooth module from the beacon, which is on my mobile phone, and that's the number I want. And I'm just going to move away my mobile phone just a couple of meters to the other side of the table. Okay, at the moment we're on minus 63. I'm just going to reset the sketch, and we should get another set of data coming out. And let's just find the address again. What did I say my address was of my mobile phone? So I think it's this one. So here we can see minus 82. So the signal to noise ratio has dropped to minus 82. So at the moment, this is looking positive. But as I said, I don't want this running on an Arduino, I want this running on the DE0-Nano. So I've come over to Quartus Prime, I'm using the standard edition here. And what I want to do, well, the first thing I'll do is add an embedded processor, because this project requires processing of serial data. So it's actually more logical to have an embedded processor to do that serial decoding and to pick off the RSSI number. So I've connected the DE0-Nano board to my Bluetooth module in much the same way as I had it connected to the Arduino Uno. So I have a transmit and receive pin, which is communicating with the Bluetooth module. I'm also stealing ground and I think it's a 5-volt pin to power the Bluetooth module. So what I need to do next is put an embedded processor onto this FPGA so it can send serial data to the Bluetooth module to program it into the right mode, and importantly to pick off serial data being sent from the Bluetooth module, which will carry with it the RSSI. Once that embedded processor is done, I need to find a way to get that information out of the embedded processor and into the hardware of the FPGA, so it can be used to manipulate the LEDs and give an indication of the signal strength. And I just wanted to show the design in a sort of block diagram form. So of course we start off with the HM10 Bluetooth module, and we have the FPGA here, which is on the DE0-Nano. And I've decided to use an embedded processor. And the reason for that is because we will need to manipulate serial data coming from the HM10 Bluetooth module. And within those serial messages, we will have the RSSI number, which will tell us the signal strength between the HM10 and another Bluetooth device in the vicinity. We'll also have to send commands to the HM10 to program it and to make it do a scan. And that kind of stuff is much easier to do in an embedded processor. So you can see I've already done it in the Arduino, and basically I'm planning just to do the same thing on the FPGA using a NIOS embedded processor. So we'll see how that's done a bit later. Now, one of the problems we run into when we use an embedded processor on an FPGA is it's not always easy to access the data from the embedded processor and then bring it back into your FPGA sort of Verilog design. But one of the ways you can do this is to use a read master. So we're lucky in a sense because Intel actually publish a working read and write master which allow you to actually read information from the memory scope of the embedded processor. So that's what I plan to use here, just to, you know, if we're bringing in the serial message from the HM10 and we manage to write some C++ code which picks off the characters which tell us the RSSI number, as we saw in the Arduino, then if we can get those characters, bring them out using the read master, and then we can use that information to control the LEDs. So we're going to need some logic to control how the LEDs should switch on. So basically how many LEDs should be switched on. And that will depend on the RSSI number. So many hours later, I finally got a working design. Now, I'm not going to sort of show you this design step by step because honestly, it took a very long time for me to get to this stage. It's it's a fairly complicated design to get working. So, well, for me anyway. But this is basically the design in quarters. This is the block diagram schematic file. So this is the top level entity for my design. And I'm going to start by showing you the embedded processor. So this is the embedded processor that's been designed. So I'm going to just go into this, open design file, and I'm going to open the .qsys file. And I'm just going to briefly tell you what's inside this embedded processor. If you haven't built an embedded processor in Quartus before, it's actually really easy. Okay, you just build up the elements of your processor from here. You have to make sure you have the NIOS 2 processor. There's various types, but that's basically what the processor is. And the way it works is it uses logic elements on the FPGA to make the processor. So it's really quite remarkable how this works. Now, you also need some memory because any processor needs memory. And you've got two options here. You can either use on-chip memory, which basically uses the resources on the FPGA to make some memory. Problem with the DE-Nano is the capacity of the chip is fairly limited, so it doesn't take long before you run out of resources. So I kept that to a minimum, and I've actually used the SD-RAM. So the DE-Nano board fortunately has an SD-RAM chip. So this is just the controller for interfacing to the SD-RAM chip, and then the stack and the heap of the program is actually run from the SD-RAM. And actually the way this works is the on-chip memory, that's actually what the read master is looking at. And when we see the code that's been written, the C++ code, you'll see that the RSSI number is being written into on-chip memory, which can then be read by the the read master. And that read master is then accessible from outside of the FPGA. You can see here, you have to write just a little bit of Verilog code to access that read master, but you can actually get out of this into the user buffer here. You can actually get out in 32-bit chunks the information that you're looking for based on the address that you look at. So that's quite interesting. Now, is there anything else on here worth talking about? Well, importantly, I've also got a UART. So this is a basic UART, and of course this is needed for us to communicate with the Bluetooth module. So that's fairly essential, and you can see the UART is coming out of the embedded processor here. So you've got the receive and the transmit pin, and these are being routed to a couple of pins on the breakout header from the DE-Nano. So you just have to make sure you attach those to the correct pins. These pins here are the SD-RAM pins. So this is for interfacing to the SD-RAM. And what else do we have? Now I've implemented a write master here. Now this is for writing data into the scope of the memory of the embedded processor. Now I don't need to use this in this project, but I put it there anyway in case it is needed a bit later on. So that covers the embedded processor. So I'm going to close this, and we can turn our attention now to the LED logic. Okay, so before we do that, let's have a look into the read master code. And to understand this, I don't propose to go through this in detail now. You'd have to read the user manual for the read master to understand what's going on here. But essentially what we're doing is we have a write base. Okay, so you can see the write base here is hexadecimal 3000. Okay, now that is actually, that correlates with the on-chip memory within the scope of the embedded processor. Okay, so that is reading from this address. Okay, and then we have the length, that's the number of words that we want to read, and that's in 4-byte sort of intervals. And basically we just do it one by one, and we read one word at a time. So one 32-bit chunk coming out at a time. And the assumption here is that the piece of code that we have has actually processed the incoming string from the Bluetooth module, and it's actually written the RSSI number to the on-chip memory. And basically what we're trying to do here is just read out what that number is. And the way it's worked out, it took a while to get it right, but the way it's worked out is it's coming out from these two signals here. And that's going into the LED logic. I can show you this code here. So it's going into the LED logic. Of course, it comes in 32-bit chunks, but really it only carries, each 32-bit chunk only carries an 8-bit ASCII word. And what we're doing here, this code is just turning the ASCII word, which is in binary form, into a decimal. So there's just a small amount of manipulation here, okay, because basically it comes out as characters. So let's say the RSSI is 67. It will come in as character 6 and character 7. You don't want it to be in that form. You want it to be 67. So this code here, if you study this code, you'll see that it's basically turning a character 6, okay, which could be that, and a character 7, which could be that, into 67. Okay, and once we have it in that form, we can write an if statement here. So this is basically an if statement, which is looking at what the value of the RSSI is, and then basically telling the LEDs, which ones to switch on and which ones to switch off. And the way it's working out here is the lower the RSSI number, the stronger the signal strength, and that means you should turn more LEDs on. Okay, and the lower the RSSI number, so in this case that would be minus 90 dBm, that's a very weak signal, then there should be no LEDs on. And then you've got ones in the middle here. So it took a bit of calibration. You know, you have to work out what the sensitivity is, and I'm sure I'll be coming back to this a bit later just to tweak these numbers. But that's basically how it works. And of course, this is going to the LEDs on the DE-Nano board. So that's basically how the Quartus design works. And apologies, I don't have time to go through this code in more detail, but if you are interested in any element of this, I'm quite happy to make a more in-depth video looking into each element of this. But that's basically the design. Now, of course, this embedded processor is not going to do anything unless it has some software to run on it. So I'm going to go to Tools, and I'm going to open NIOS 2 Software Build Tools for Eclipse. And this is the design environment for writing software to target embedded processors in the Intel family. And you can see I've already written some software here. I haven't tidied this up at all since last time I used it, but this is basically a piece of code, and this is not Verilog code. This is now C++ code to target implementation on that processor. So you can see it's actually behaving in much the same way as the Arduino sketch that we wrote earlier. So you have, first of all, printfs. Okay, so this is sending these characters over the UART. So these are the commands that we worked out before that we needed to send to basically program the Bluetooth module to do a discovery scan. Okay, this is the important one. Now I've introduced here this command, getchar. Now that's just waiting for a response, because I realized without this, you can actually send the next command before the module is ready for it. And the module will actually send a reply message. So if you wait for that reply message, okay, and that will happen, the software will know that's been sent, because it will move on from this line of code. After that message has been sent, then it will go to the next command. And then you can be sure that the module is ready to receive that command. Now, what I've done here is I have a while loop. I'm using this getchar command to actually receive a character which is coming into the UART. And what I'm looking for here is the address of my mobile phone. Okay, and this is 3 consecutive characters on the Bluetooth module on my mobile phone. And if you get these 3 characters in a row, then you know that a message has been sent by that device. Okay, it's very unlikely that it's going to be a different device. Now, I recognize that if you were to write this design to work in a more general sense for any Bluetooth module, then you'd have to make this code a bit different. But for now, I'm just going to make my life easy and just target the Bluetooth module on my mobile phone. Okay, now this is the tricky bit now, because we need to pick off the RSSI number. But you can actually do this using trial and error, because what you can do is actually, once you get these 3 characters, you know that it will be a definite number of characters later that the RSSI number will come as a character. And I worked out that that number was 29 and 30. So these 2 actually give you the RSSI number. And what I've done here, now this is the important bit, I've used this command. It's IOWrite, so IOWR, and this will write this into this base address with an offset of 2. And then the next one, it will write to this base address with an offset of 3. And these are the RSSI numbers. Okay, and if you recall, if I go back to my Quartus design, this readmaster is actually looking at that precise location to get those numbers back out into the Verilog code where it can be manipulated and where it can actually control the LEDs. So that really is the really important part of this code, is actually this bit here, okay, because that's writing that data coming in over the UART into a known region of the on-chip memory. And that's basically it. There's not that much more to it. Now, it is doing one more thing. I wanted this to work in an automated way. So once we have one message come through, one scan is complete, you have to make the device do another scan. And I just have another nested if statement here. So if we get these 3 characters, that means the scan has come to an end. And we basically say, okay, do another scan. This command makes the Bluetooth module do a scan. And the whole process starts again. So that is basically the code. So I think we're ready now to take a look to see if this is actually working. So once I'm ready to basically put this code onto my device so it runs on the embedded processor, I just need to make sure the device is programmed, right-click, and run as NIOS 2 hardware. And that will put that program onto the embedded processor. Oh, we've got a small problem here, so this problem can be easily solved if you just refresh connections. This is the first time I've run it today, so hit run again, and it will upload the program, and this software will run on my embedded processor. So give that a few seconds to start running. Good, okay, and I just wanted to show you how I'm using Signal Tap in this design. So this is my Signal Tap window, and I'm using Signal Tap to program the device. But as I've explained in other videos, Signal Tap is a really invaluable tool for seeing what's going on inside the FPGA. And really, with a design as complex as this, it's really difficult to make any progress without something like Signal Tap. And the way Signal Tap works is it's like a real-time signal analyzer inside the FPGA. So it actually puts logic inside your FPGA, which is basically realizing a signal analyzer. And you can see these signals in real time. So you can see the important ones I'm looking for, stamp 4 and stamp 3. They are coming out of the readmaster, so they should include the digits, the RSSI digits, and you can see that's actually 59, and it will change 61. I've got the phone very close to the Bluetooth device here, so the RSSI signal is quite strong. And then you can see this is verifying to me that I'm actually converting those characters 5 and 6 into the number 56. And here you can see the result of the if statement, which is go into the LEDs. So just wanted to just make it clear how useful Signal Tap is in a design of this nature. So I've actually got the program working here. So I've got, in real time, I've got the Signal Tap window open, so you can see what's going on inside the FPGA in real time. And you can see as I get closer, before I move on, the Bluetooth device in my phone is the device taking this video. So, you should see as we get closer, you can see the LEDs are all on, and the RSSI number is fairly strong, so -61. But as I pull away, we should start to see those LEDs turn off. Now, one of the disadvantages of this is the response time is pretty slow. So that's one thing to try to improve, but that's a limitation of the Bluetooth module. as I move away, you can see the LEDs. So I'm over a meter away here, and you can see the LEDs switch off. And I'll just slowly move back in, and we should see the LEDs slowly move back on. So as you can see, if this was a person, this would be indicating how close you were.